Time. Welcome back to everybody. Let's talk one last time about the U substitution. That's what we've been doing, and then we'll get on to something different. The U substitution, like I said at the end last time, there's like one extra trick that I wanted to talk about. We did one example at the end last time. Let's try one more, and then I got one for you all to try, and then we'll move on to something completely different. How about... How about this one? X over 2x plus 3 to the 5. All right. This requires a weird trick, although if you didn't know that, you should just begin, start as you usually would. Anybody want to suggest what should I choose for the U? Yeah?
2x plus 3.
2x plus 3, yeah. If you see parentheses, the inside of the parentheses is always a good idea. So I'm going to go U equals 2x plus 3. Great. And next we do the du, which is just 2 dx. That's the derivative of the u. All right, as I usually do, I'm going to divide the 2 here, write it as 1/2 du equals dx, just because that's pretty much always what you want to do. All right, and now let's try to do the substitution. So I'm going to plug in what I can. On the bottom is just u to the 5. Up top is x. Not sure what I'm going to do with that yet. But then dx, I can see over here, dx is 1/2 du. So I'm going to put that here instead of dx, 1/2 du. All right. And what makes this one hard is that we have a leftover x here, and it's not really clear where we're going to get this x. Like, you have to write everything in terms of u's. So I want to somehow write the x in terms of u's. Like I said, we did one at the end last time. Anybody remember how to do it? We can do this similar thing here. Yeah?
You solve for x using what u equals.
Yeah, right. Up here, you can solve for x in terms of u. So that's what we're going to do. From there, solve that part for x. In a usual u substitution, this is not necessary, but this is a hard one, in which case, it is necessary. This is what makes this a hard one. So from there, I'm going to solve for x. It says u equals, maybe I'll just do this on the side here. U is 2x plus 3. I solve for x by subtracting the 3. So u minus 3 is 2x, and then divide the 2. I guess x equals, I'll write it as 1/2 u minus 3/2. So you got to divide 2 everywhere there. All right. That's what the x is, and that's what I'm going to plug in inside the integral there, where it says x up top. We put that stuff. So this is integral. Would you mind if I take this 1/2? This 1/2 is going to pull all the way out of the integral because it's just a multiplied constant on the inside. So let's put that outside. And then I got 1/2 u minus 3/2 over u to the 5 du. All right, that was the hard step, I suppose. Although it looks kind of crazy at this point, but at this point, what we would typically do is I see u to the 5 in the denominator. I'm going to write that instead of dividing u to the 5, I'm going to write it as times u to the minus 5. So half will just stay out front forever until it's over. Instead of dividing u to the 5, I write it as times u to the minus 5. So it's that business, and then times u to the minus 5. This is another typical trick that we do all the time. Make sure you have those parentheses there, because my next step is I'm going to distribute. If you forgot the parentheses, I know I've heard on the playground there's some parentheses haters out there. I hope that none of you are parentheses haters. You need these parentheses so that you remember to distribute. So I'm going to distribute like so, right? We get 1/2 out front. And then, remember, when you distribute in this situation, you should be adding the exponents. Like, this is a u to the 1. U to the 1 times u to the minus 5. I add the exponents and I get minus 4. So this is going to be 1/2 u to the minus 4, and then minus 3/2 u to the minus 5. Like that. And now we are ready to do the integrals. Everything now looks more or less like polynomials. We got weird coefficients and negative exponents, but it doesn't really matter. We can just do the integrals at this point. All right, so do the integral. 1/2 stays out front with some big parentheses, and then I'm going to do antiderivatives on each of those two things on the inside. 1/2 u to the minus 4 becomes 1/2, and then 1 over minus 3 u to the minus 3. Remember the rule, you increase the power by 1, so minus 4 becomes minus 3, and then you got to divide by the new exponent. And then same thing on the other part, so it'll be minus 3/2, 1 over minus 4 u to the minus 4. Right, and that's basically it. One very last step. Anyone remember? This is kind of a technicality step. It's always easy, but you got to do it at the end. Yeah.
Put you back in.
Put the put the x's back in, or put the u back in, however you want to say it. This u I want to write instead in terms of x. So u is 2x plus 3. So wherever I see u here, I put 2x plus 3. It's going to look a little crazy. That's all right. Maybe I'll just combine those fractions there by multiplying. 1/2 and 1/3 is 1/6. So this is 1 over minus 6. And then the u is 2x plus 3, like that, right? And then the other one is going to be 3 over 8, 2x plus 3 to the minus 4. Like that. I multiplied the fractions together. I don't really care about that, but this is what we get. That's a hard one, in my opinion. Any questions about all that? I think you will find out if you get it or not by trying to do a similar one. All right, here's a similar one. See what you think. As usual, I'm going to come around and see how you're doing. Very similar, although here you actually have like two different things that look like they might be appropriate for the u. I'm going to take the one inside the third power there, but that's just me. Actually, you have to do it that way if you want it to work out. All right, see what you think. It's kind of like the one I just did. A little easier, maybe. Talk to your friends about it if you like. That's good. Yeah, so you should start plugging in here to just put u here. So u cubed, right? And then like the first step in the substitution would be to replace this one by u, because u is this nice thing is u. So I said this as u cubed.
It's like like for here, use the plug-in.
Yeah, right. So you put all the other stuff with it.
Yeah, 12 plus 12. Whatever. Yeah, that's what I did. It's just 3 plus 12. And
Now, you want to change dx into something other, that's just easy in this case because dx equals du. You got to do this, change that into u. Yeah, that's something there.
And you just substituted this for du. Yeah, basically. One, yeah, because
like this. Now you want to somehow change this to something.
So yes, so if I'm just like you take this, it's called U plus 3 over the So you distribute this out?
Yes. Yeah.
That's what I thought, but I was trying
So you just plug back in that? Well, so like from here. So right down. Oh wait, no. Wait. Yeah, U plus 12. I mean, I distribute myself. Oh, no, yeah, I distribute like so. U to the third times U to the fourth plus 12 to the third. So
I forgot about you over there.
yeah. Oh yeah, yeah.
Yeah, I think so. These,
Yeah, it's just I'm parentheses and then and this one is pretty much
these guys are all
oh, okay. Yeah,
use everything. So you can take U plus 12. And then you actually have to distribute it.
Something like that.
Yes. Yeah, I think so.
And then should we simplify it a little more?
No, I mean the last step would be to put the
To put back the
X.
X in there.
Something's not quite right.
Oh yeah.
Like the 3 should increase to a 4.
Here I have it 4.
Yeah, actually,
this one.
both of these, like this 4 should increase to a 5. X minus divided by 5. Maybe you're doing the derivatives.
Oh yeah. I don't know what I did.
Yes.
This was a put the X back.
But usually, so this increases the.
Yes, it's
All right, let's talk about this. Folks seem to be doing just fine. We go u equals x minus 7, and then the du is just dx. And just because I know we're going to have to do this eventually, you can solve for x here, and you should say x equals u plus 7. All right? And now we're going to plug everything in here. So I, first of all, put in u cubed du, right? That's because x minus 7 just is u. So I replaced it with u. And dx is du, so I plug that in. What do I do with x plus 5? That's where I use this part where I solved for x. So this x here becomes u plus 7. So I go, this is like u plus 7 plus 5 in there, and then u cubed du. And then the u plus 7 plus 5, you can just add that up. It's u plus 12, and then u cubed du, and then I'm going to distribute. U plus 12, u cubed du, and then this will distribute like that. So we multiply u times u cubed is u to the 4. This is still not doing the integral yet, just resimplifying every time. U to the 4 plus 12 u cubed. And now finally we can do the integral. U increase the powers by 1. So u to the 4 becomes u to the 5 and a 1/5. So this is 1/5 u to the 5 plus 12 over 4 u to the 4. And I don't want du anymore. I want the plus c. All right. And then you just plug the x's instead of u. So u is x minus 7, and then that'll be my final answer. X minus 7 to the 5 plus 12 over 4 is 3, and then x minus 7 to the 4. That's that. All right. As I was going around, it looked like most folks were doing just fine. So I hope that seems all right for you. this is the end of the U substitution. You will have some chance to practice more on the homeworks. By the way, I'm going to post the homework after class today. It will be due on Wednesday, like I said before. All right. Great. Here ends the U substitution. Okay, let's go on to the next thing. That the U substitution was number 2 on the big list. And that was the last of our review topics. So I do assume, I have been assuming that you've heard of the U substitution before. Everything from now on, I'm just going to assume that you never heard of it. I mean, maybe you have, maybe you haven't, but I'm going to act like you have never heard of any of this stuff. This is number 3 on the big list. It is the area between curves. The area between curves. All right. This is, everybody knows, the area under the curve is the integral, right? So this, integral f of x dx from a to b. What does that mean? It means the area under the curve, which would be something like if this is my f of x and a and b are numbers along the x-axis. It means this area right here, right? Area under the curve. It's the area under the curve. And we are going to do, like, our next 3 topics on the list, at least 3, maybe exactly 3, are all about variations on this basic idea. So this is the fundamental, basic idea that I hope you're all familiar with. You better be familiar with. And let me just say one more thing about where this comes from. This is based on what we call Riemann sums. This is something you probably did sort of like a lot of examples with Riemann sums kind of by hand in your Calc 1 class. We're not really going to get into it, but I will remind you of the basic idea. If you have this kind of weird curvy shape, the idea behind how you find this weird area is you chop up this area into a bunch of little bitty bits, and along each of those bitties you draw a little rectangle, and then you add up those rectangle areas. I hope you remember doing this. Like I said, I'm not actually going to get into the weeds of this, but you can add them up using the left endpoints or the right endpoints or the midpoints. I hope this all sounds familiar to you. This is based on Riemann sums. You add, come on now, I'm trying to zoom. You add these rectangle areas, and the widths of the rectangles are all some little bitty width, which we usually call delta x, and this is very small. And then the heights are all f of x. Like the heights are all just like determined by how tall the graph is where each one of those rectangles are, right? The height of the graph tells you how high the rectangle goes. Those are the heights. You have some kind of very small width, which we usually call delta x, and then we add them up. Then we do some kind of big summation where you go the height times the width each time. This is the height. This is the width. And this gives you an area, right? Because the area of a rectangle is the height times the width. And I have that big sigma. That means I'm adding them all up, all right? This is a very vague idea of what the integral is used for. And this we write as this weird thing, f of x dx. Like that's actually why when we write an integral, it's why we write this dx. We imagine this dx somehow is representative of these little widths of all these rectangles. And these rectangles have that height. And then this weird looking symbol is actually meant to look like a S, which is the sort of Northern European version of the Greek letter sigma. All of this is meant to look kind of like that. All right. But and none of that really matters when you're doing these problems. But I'm just giving us a little review of where the area under the curve comes from. It comes from adding up all these little rectangles, all right? Why I mention this is because, like I said, our next three major topics are all variations on this basic idea. So the basic idea is adding up these rectangles. Their heights are all equal to f of x, all right? Now, this gets you what we call the area under the curve, right? But this is what I want to talk about today, the area between curves. So the idea is we want something like two different curves. Maybe here's f and here's g, and I have the area from A to B like this. This is what we call the area between curves, all right? This is probably what you thought it meant. I mean, this is not very strange terminology. This is called the area between the curves, all right? And the question is, how do we find the area between the curves as an integral? And this is why I refreshed our memory about all of this business up here, about the heights and the widths and whatever, all right? The big difference here is, instead of putting rectangles sort of from the curve all the way down to the x-axis, really the rectangles that we would be interested in here would go from the top down to the bottom of this curve. So we would, if we wanted to work this out, we'd do rectangles. I'm going to try to sort of zoom in on this picture. If here's f and here's g down here, this time my rectangles would look like this. They sort of go up to f at the top and down to g at the bottom, right? And the important part here is these heights, they aren't f of x. They are now f of x minus g of x, all right? The heights of these rectangles, the top is at f, the bottom is at g, and so if you want the height of that, it's like the distance, the distance from up here to down here, you'd subtract those two numbers, all right? So the heights of these rectangles is f of x minus g of x. Otherwise, everything else is totally the same. All the widths are still going to be just delta x's, and we go from A to B on one side. So what I'm saying is the area between curves is really just the same exact stuff as the area under the curve. It's just that the heights, we're going to use f of x minus g of x instead of just f of x for the area under the curve. All right, so this little in conclusion. So for the area between curves, I'll write it out. The area between f and g from x equal a to x equal b is, and this is a formula that I suppose you should memorize this formula. I mean, there's not a lot to it, but it's this. It's just the same as the area under one curve, only I subtract them like that. Why do we subtract them? It's because of all this what I just said. It's because you do the rectangle thing. Again, it's all the same except for these heights are now f minus g instead of just f. All right? The area between curves, this is the formula for the area between curves. Maybe I'll put this in a box. I'd say you should memorize this, but I mean, there's not much to it. You're not going to have to like sit down and memorize. It's always f of x minus g of x. And maybe I should say specifically where f is the bigger one, g is the smaller one. I mean, when you look at the curves, f is like up top and g is on the bottom, right? If you subtracted the wrong way around, everything will just be negative when it ought to be positive, all right? F is the bigger one, g is the smaller one, all right? This sometimes they say this is biggie minus smalls, if you will, all right? Who would ever do smalls minus biggie? Come on now. Obviously, it's biggie minus smalls, all right? It's the bigger function, and you subtract the smaller function. All right, this is the basic idea, and otherwise you just have to sort of do the integral. So, as usual, I got a couple examples, and then I got some for you to try, and then I have some kind of variations, all right? There's sort of easy ones and then slight variations. Let's try a fairly easy one. Let's find, okay, here is an example. Find the area between x and x squared. Where the graphs cross one another. The area between x and x squared. Now, if these are really weird functions, you're probably going to have to graph them on your calculator so that you'll know like which one is the bigger and the smaller. Although for our, and on the homework you might want to do that. For our examples on our quizzes and tests, you're not going to be using a calculator. So this is an example of one where these functions, I would expect you to be able to know what the graphs look like. I hope everybody knows the graph of y equals x and y equals x squared. So I'm going to graph these together. Y equals x looks like just a straight line, like so, right? This is x. And then x squared looks like a parabola going up like this. Something like that. This is x squared, all right? I hope that you would be able to draw these curves without using a calculator if this was on our quiz or something. All right. I would expect you to be able to draw other variations of lines and parabolas. Parabola, you should know that, for instance, if it was instead x squared plus 1, that would be the same parabola but like moved up by 1. You should know those basic kind of graph transformation type things. I wouldn't expect you to graph a random other kind of polynomial, but just simple variations on parabolas you should know how to do. Like minus x squared is the parabola facing downward. All right, you get the idea. Anyway, the area that I'm talking about, now that you can see the picture, you should realize the area that I'm talking about is this area in the middle, right? In between these two curves. And so you should decide for yourself, okay, so we're going to do, it is the area from A to B, f of x minus g of x. That's the formula, right? We should decide what are the a and the b and what are the f and the g. Now, the f and the g are x and x squared, but you have to decide for yourself which one is the bigger and which one is the smaller one. So maybe... can someone say which is, you can tell just by looking at the picture. Which one's the bigger one? X or x squared? Are you not saying it because it's too simple? I'm talking about right where this part is. Which one's bigger, x or x squared? What do you say?
X.
X. Yeah. How did you know that?
It's above.
Because it's above. Yeah, that's what I'm asking about. I think probably everybody knows this, and they're just not saying anything. Yeah, it's the one on top is what I'm talking about here. That's x, the straight line. X squared is the one on bottom. All right. So the bigger one is x. The smaller one is x squared. This is a little weird because usually I think of x squared as being bigger than x, but only in this little region here, the x is actually bigger than the x squared. All right. What about the a and the b? The a and the b. So what I'm going to do is eventually bigger, which is x minus x squared. Right. That's the integral I have to do. What about the a and the b though? The a and the b are the x values of the ends of this picture here. Right. That's the a. That's the b. The x values. I think you can tell right on the picture, the a is 0, right? Because that's where, you can see those two curves are intersecting at the origin, which is x equals 0. What about this point here? You have to ask yourself, you could try and just kind of like common sense this. Is there a value of x where x and x squared are the same number? You could say 0, and that's why this is here, because 0 is the same as 0 squared. There's another number, though, where the number is the same as its square. Anyone know? Show me the fingers. I see some people showing, yes, not the bad one, the good one. 1 is the answer. 1 is the same as 1 squared, right? So that's where this other value is. B is actually 1. The integral is from 0 to 1. All right. This one you can kind of common sense out those two values of 0 and 1. But sometimes you may not be able to. I mean, I don't know if you found it hard to just look at the graph and know these are 0 and 1. You might have to find the intersection points by hand. Now, in this example, you can kind of figure them out. But in some examples, you'll have to actually work it out, like if the intersection points happen to be at weird numbers or something. Anybody remember, this is something I'm sure you did in high school or before. How would I, if I just asked you, I have two functions, how do you find the where they intersect? There's like you learned how to do this with functions generally. Where do the two curves intersect? Anybody remember? This is, you want to set the two curves equal to each other and then solve for x. So to find the intersections here, if I couldn't somehow figure them out just by common sense, we set the curves equal and then solve for x. So in this example, I would say x equals x squared and then solve that for x. This is a little weird, but this is a polynomial. The best way to solve this for x would be to write everything, set everything equal to 0. I would say 0 equals x squared minus x, and then factor. All right. To factor x squared minus x, you could just factor x out. And now that is a factored polynomial set equal to 0. That means that either the first one is 0 or the second one is 0. So x equals 0 or x minus 1 equals 0, which means x equals 0 or x equal 1. Those are the 2 points. All right. So this is, if you somehow weren't able to figure the points out just by looking at the graph, you can actually work it out by hand and you'll get the correct values. 0 and 1 are the correct values. All right. All right, anyway, all of this just boils down to this integral, which is actually an easy integral to do. So we might as well actually do it. These problems, typically, the hard part is just like setting the whole thing up. And then actually doing the integral is usually not all that difficult. So the area is integral 0 to 1, x minus x squared dx. And how do we do this integral? It's just ordinary polynomial. So the integral of x is 1/2 x squared minus, and then I go 1/3 x cubed, and I plug in 1 and 0. And then we plug them in. So you plug 1 in everywhere for x, and then you plug 0 in everywhere for x. So it's 1/2, 1 squared minus 1/3, 1 cubed minus, and now I go back, plug zeros. 1/2, 0 squared minus 1/3, 0 cubed. And that's the answer. These zeros inside the parentheses, that's just all 0. And at the beginning, it's 1/2 minus 1/3, which I guess is 1/6. I don't really care about that, but that's what it is. All right, this is the area between curves. This was an easy one in my opinion because you can kind of do a lot of the parts in your head. All right, I mean this stuff is not terribly necessary in this easy example. Any questions about that though? All right, I got 2 little variations. So that, in my opinion, is an easy one. There are 2 kinds of variations which you may encounter. Let's just try another one. I don't think we need much of a preamble here, but you're going to see why this example requires some extra steps. So your job in this case, find the shaded area. On our tests or whatever, you're not going to have a graphing calculator, and so I might just like show you the picture so that you don't have to deal with making the graph up on your own. So here is a picture. This one has 2 lines, but they're in sort of weird arrangement. Trying to make them look good. All right, this one up here is y equals 2x plus 1, and this one down here is y equals negative x. And the shaded area, I didn't shade it yet, but this is it. Back here, so this is -3 back here, and then going up to +2 over here. And this is the area I want. That guy, this sort of bow tie shape. All right, find the shaded area. All right, we're going to do the same thing from before. It's the integral, and I go the bigger minus the smaller. What's interesting about this one that didn't happen before is that the two curves cross in the middle. So I will say what's interesting about this one. This one has a crossing in the middle, which the other ones didn't. Why that matters is because actually it means that the bigger versus the smaller kind of flips. Like over here in this part, this one is bigger, 2x plus 1 is bigger, but on this side over here, the other one is bigger, right? So when I do bigger minus smaller, it actually, there isn't one that's bigger all the time because their roles, bigger versus smaller, flip-flops in the middle. So this has a crossing in the middle, which makes it harder. So, come on. What's happening here? So, we must split it. Split it. All right? The idea is this sort of bow tie shape, it has that triangle on the left and that triangle on the right. We just have to do those two triangles separately, find their areas, each one of them, and then add them together to get our final answer. You have to do them separately because the bigger versus the smaller is different on both of them. So you can't just do them both at once. All right? So we do these parts separately. What I mean this part versus, this part, right? Because they have different biggers and smallers, which means when we write out the integral using that formula, they're going to be two different things that we got to do, one versus the other. All right. All right. This is not so hard. I mean, I suppose we have to do it twice, but that's not such a big deal. One little problem. Let's just start with the one on the left, right? Let's do this one first. It's going to be the integral of the bigger minus smaller. Now on that side, the left-hand side, the bigger is negative x. So here I'm going to say negative x minus 2x plus 1, right? Because I'm looking at this side here, the bigger one is this line, which is minus x, and the smaller is this line, which is 2x plus 1. So this is the bigger minus the smaller. We do have to do a little bit more work to get the a's and the b's. The a is the left side, and the b is the right side, which is that blue point. But actually, I didn't tell you what that blue, where is that blue dot? So the a is at minus 3. Here, this is, well, it's really this x value right there is what we're going to use for that point. All right. So we do have to do one extra step here, which is to find the location of that blue point, which is not at the origin. I mean, it's off to the side a little bit, and I did that intentionally. Anybody want to suggest how can we find the blue point? This is similar to something that we just mentioned. Yeah.
Set the negative x and then 2x plus 1 equal to.
Yeah, right. Set the two equations equal to one another. This is always how you're going to find intersection points on a graph. We set the two equations equal to each other. So here, to find the crossing point, I'm going to set them equal. That is to say, 2x plus 1 equals negative x. And this is a fairly ordinary thing to solve for x, right? Maybe I will, I don't know, put all the x's on the right-hand side. It'll say 1 equals negative 3x, right? If I subtract 2x on both sides. And then solve for x, divide by negative 3, x is negative 1/3. Which actually, I mean, I suppose that looks pretty good on the picture, right? It's negative, which is what I expected. All right, that's the crossing point. And so to do this, at least this part of it, I go My values are -3 and -1/3. Like that. All right. This is now a fairly straightforward integral. Let's just do the integral. You don't have to do any tricks here, use substitution or whatever. Actually, I mean, in some examples, in theory, you might have to do a substitution here, but we don't. This is slightly weird. I have parentheses with a minus sign, but you can just distribute the minus sign here and sort of add everything up. So this is really not anything fancy. So I'm going to say minus x minus 2x minus 1. That is distributing the minus sign. Don't forget to make that a -1 there. And then you can do the integral directly here, although we can add them up. You know, minus x and minus 2x, they can add together, and I get minus 3x. I just try and make it simple before we actually do the integral. Minus 3x minus 1. That's just a little simplification. All right. And now let's do the antiderivative. Can somebody say? Maybe I could hear from one of the ladies. I don't hear from the ladies that much. I mean, in this class, of course. My DMs be going crazy. No, that's not actually true. I have a wife and a daughter, so they go crazy sometimes. What do you say? The antiderivative? It's not a hard one, ladies.
-3x squared over 2
Mm-hmm.
plus x.
Yes, great. Negative 3x squared over 2. The x becomes a x squared, and then I divide by 2. And then the -1 becomes a minus x. Thank you. And then I got to plug these numbers, right? And then we get, you know, whatever we get. So this is minus 3/2 negative 1/3 squared minus negative 1/3. Remember to get all your minus signs proper. And then subtract minus 3/2 negative 3 squared minus negative 3. Like that. All right? This is a number, whatever that is. That's the area. Now, we're not done here. This is not the end because that's just the area of the left side. All right? Now we have to do this again for the other side. And we do have to do all this stuff again, although it's more or less the same stuff. So once you do this once, it's not so hard to do the rest of it. So this is the left side. We're not totally done here. To get the right side, all right, that's you know, this shape, right? So now I'm going to do this one. It's basically the same stuff. What's the difference? I would say, okay, it's integral. One difference is instead of it's the a and the b, right? Instead of, it used to be -3 up to negative 1/3. This time I go negative 1/3 up to 2, right? So that's one difference. And then the other difference is, what do we put inside the integral? It's always the bigger minus the smaller, but on this side, the bigger it's the other way around, right? So the bigger this time is 2x minus 1. And then the smaller is minus x, like that. All right? So this is the setup for this one. The bigger and the smaller is the other way around, and we have different boundary values. But we'll see. Well, let's just do it. We'll see. After you simplify on the inside, this is 2x minus 1 plus x. And then you could do the integral here directly, or we could just add up the x's, right? I have a 2x and also a plus x, so I can add them up to get 3x. Sorry, I feel like something ain't right. It's 2x plus 1. Yeah, I just copied it wrong. Thanks. It's 2x plus 1 on the original picture. All right, I'm going to combine the x's. 2x plus x, I can put them together to make 3x plus 1. And you'll notice this at this point is basically the same as what we had on that side. The only difference is it's negative versus positive. That's because it's the same two functions. We're just subtracting them in the opposite order. So this is what you should expect to see, basically the same integral both times, it's just flipped around. All right, and then we do the integral. We're almost done with this one. So it's now 3/2 x squared plus x, just like she said before, but they're positive instead of negatives. And then we plug in minus 1/3 to 2. So this is 3/2 2 squared plus 2 minus 3/2 minus 1/3 squared plus minus 1/3. There you go. All right. And this is the right side. A lot of little details there. Okay, so what's my final answer? It's the left side plus the right side. So the total area, and this, you know, I don't really care how you write this. Would you mind if I say something like, it's this part plus this part, right? I'm sure you could copy all of that down again if you like to, but it's this part plus this part. And, you know, when you're doing this on a test or something, it's totally fine with me if you want to write it in that way. I know what you mean, and there's no need to copy down all the little things. If you're doing this with a calculator, of course, you can just add this all up and then actually add the two answers together easily on a calculator. By hand, it's a pain. All right, this is the full area. All right, I got one like that for you all to try. We do have, we got about a half hour left. There's one more variation, but maybe we'll try one like this first, and then I'll talk about one more variation on the area between curves. But here's another one where I will draw the picture for you. The graph here is, this is a parabola going down. This is y equals 3x minus x squared. That's an example of one where I would not really expect you to draw that by hand on a test or something. That's the parabola. Sorry, I'm going to label it over here because I'm about to draw another line which will kind of intersect that like this. And this is 3 minus x. That's a straight line. All right? And the area that I want you to find is this here and here. All right? So this is another one where you're going to have to split it apart into two parts and then add those two answers together. All right? See what you think. One of the first things you're going to have to do is figure out where this intersection point is. Yeah, put everything on one side and then factor. Yeah, you have to put everything on one side so it's all set equals 0. And then factor. This actually. How's it going? Very nice picture. Yep. Good so far.
X squared plus 4x minus minus 3.
No. We have that x squared is 2x minus 3. So what do you have? Oh no, you're right, actually.
Being multiplied to. I would suggest multiply to. It shouldn't be plus 14. Well, one of those adaptive practices. That wasn't fair. It's like
X.
Can't be though.
This is.
It should be 3.
It is one. Stop gaslighting me. You said green.
Because the words after the right side, it multiplies into
Yeah, I think it's multiplied on the right side and it adds up in the middle. Yeah.
So yeah, that makes sense.
It would make sense 3 and 1. Because there's a negative sign, that means it's 2 different signs. It would be plus and minus.
Yeah, but yeah.
I think we did.
Plus.
No, but like,
No, plus on which side?
oh, I was doing
Yeah.
before I thought of it as multiplying this as so no, it was like I like to see the one
Oh, you know what?
It's minus 3.
because
Well, depending on which side. It depends on which side you sold it.
because like I think it's like two soup, you know what I mean? Oh wait, so that's the last one's like 3 times.
Oh, it's which one? One is minus x, the other one is x.
I was looking at that.
And then we said,
Yeah,
it would be minus x times x. That's clear. Minus x times x.
Whatever you think.
Plus x plus 3x. Is 3x, that's 4x. And we think minus 3? Yeah.
X plus 3. It's X minus 1.
Minus x plus 3.
Minus X plus 3.
Yeah, exactly. We feel you just hear that or?
Yeah.
I think so.
Oh wait, no.
Oh, that was from the point.
Yeah, so it's
Oh, and then we solved it. And then we did minus x plus 3.
How you guys doing?
Right there.
What?
Same minus x plus 3, x plus 1. X minus 1. Yeah, minus x. I win that. Yeah, so
Like mine.
that's 4x. And here we have negative x squared minus 3. We have 2 signs here. So plus 4x's and minus 3. That doesn't that
Yeah,
mean?
it's because this minus here.
Uh-huh.
Yeah,
it's oh yeah, it's
in my opinion, it's a lot easier just to multiply this by minus 1 to make it like having a negative in front of x squared.
yeah.
How's it going? Yeah, this is good. Yeah, you got it.
Here's just x equals 3 for the first one. in x squared.
Oh,
Wait, yeah.
And I would suggest putting them all to the side, because I don't like this from the x squared. But anyway, from here, what you can do is you want to choose your two values.
There were 2 points for this one.
But yeah, it won't work here.
Yeah, I'm sure.
All right, can we talk about this one? I see people have made varying amounts of progress, but I did have one more thing I wanted to cover today. So let's talk about this. We should begin by finding the intersection point in the middle. And also, I didn't mention it before, but really you do also need to find the intersection on the end here, right? This point in the middle I don't know, and also this point over here is sort of the end of the second area. We need to know what that point is. But anyway, we're going to do this by solving, setting these things equal to one another and solving. So it's like that. And now I want to, because this is a quadratic, I'm going to have to solve by factoring. I'm going to put everything on one side, set equal to 0. And you can, of course, decide for yourself how you want to put this. I like for my x squared to be positive, though, when I factor. I'm not into negative x squared. So I'm going to put everything, as written here, I'm going to move everything over to the left side. It will say x squared. And then for the x's, I had minus x. I'm going to subtract another 3x, so this will be minus 4x, and then a plus 3. I saw some people got messed up in here somewhere, which makes it impossible to factor if you screw up the algebra right there. All right. But anyway, now I can factor. That's this thing. You may want to refresh your memory about factoring, by the way. This kind of simple factoring we're going to do all the time. So if you're a little rusty on that, it's all right for now, I guess. But this is important in this class. I want to, it's going to be x plus something, or maybe minus. I want these two numbers. They have to multiply to be 3 and add to be negative 4. Because this is going to be negative, I want to see two negative numbers here. And they should be 3 and 1, right? They would multiply to 3 and add up to 4. So this is going to be minus 3 and minus 1, however you want to write it. All right. And then to solve for x here, you just equate both to 0, right? So that means x minus 3 is 0, or x minus 1 is 0, which means x is 3 or x is 1. These are the 2 points. And you should be able to look at the picture and verify that that looks reasonable. So this is 1. That's 3. This is what we've determined. And that does look reasonable to me on the picture. All right. Any questions so far? I saw a lot of people getting sort of bogged down in this part and never really got to the integral part. But this is, unfortunately, this is kind of the easy part. This is like, if you remember how to do this stuff, then you remember it. All right. Let's do the two pieces then. So I'm going to do the piece on the left first. Is like sort of this one. I have to do the integral from, what are the boundaries here? The left edge of that is going to be 0, because it's over here at x equals 0. And then up to 1, that's the first intersection point that we found. And then I got to do bigger minus smaller. The biggie here is the straight line part, which is 3 minus x. And then subtract, the smaller is the parabola part, 3x minus x squared. All right. And now this, we just have to sort of, I would simplify the inside a little bit and then do the integral. So simplifying the inside, 3 minus, let's distribute the minus sign first. 3 minus x minus 3x plus x squared. And then I like to write it sort of like a good boy writes a quadratic polynomial. You don't have to rearrange it all that much, but this is how I like to see them. All right. And now do the integral. We do the thing with the exponents. So it's 1/3 x cubed minus 4 over 2x squared plus 3x. And then I plug zeros and ones. So 1/3, 1 cubed minus 4 over 2, 1 squared plus 3 times 1. Subtract all the same stuff with zeros. Like that. All right, that was the area on the left side. All right. maybe I saw, like, as I was going around, most people didn't even get this far. So maybe could I give you guys another few minutes to try and do the other side? It should be very much like this, given what we've done so far. And maybe I just won't do what I had planned on doing before. See if you can finish off the other side. I'm going to walk around again. I know some of you already finished it. You can just feel superior for the next few minutes.
Yeah.
How you guys doing? You should. This is kind of backwards. Yours with the smaller one. The smaller number down here.
Oh.
It's from 1 up to 3.
I just put it up and see like I have the numbers. So it should be like this.
Yeah. And then you go function minus.
When you got to distributed this.
No, that's
Yeah. I don't know where the x squared first and then 3x plus x in 4x.
4x minus 3.
Yeah.
minus. Yeah, then. Make sure you put parentheses because you have to distribute it. When you say minus here. You guys good?
Yeah, I think so.
Yeah, I think so.
All right. All right, can we talk about this? People seem to be doing fine with the rest of it. So this time the integration, the boundaries is from here to here. So that's from 1 up to 3. So I go 1 to 3. And then the bigger minus the smaller. The bigger is the parabola. So that's 3x squared minus, no, 3x minus x squared. That's the parabola part. And then the line part. The parabola is the bigger and the line is the smaller. All right, and now we just have to do this integral. I would distribute the minus sign first. 3x minus x squared minus 3 plus x. You can add the x's together if you like. 4x minus x squared minus 3 is how I would write this. And you will notice, if you care to notice, this formula inside here is very similar to that one. It's just the signs are all backwards, and that's actually what it should be. Anyway, do the integral. I go 4 over 2x squared minus 1/3 x cubed minus 3x from 1 to 3. And this is 4 over 2. 3 squared minus 1/3 3 cubed minus 3 times 3 minus this stuff with ones. There you go. All right, so my final answer would be this part plus the other part. You know, this one plus this one. Those two parts. All right, anybody got questions about that one? All right, maybe I'll give us a little intro to the last variation. So these are the very basic area between curves thing. You can hopefully get by just doing one of these integrals, right? That this one here was a very easy one. One variation is when the curves cross in the middle, you have to split it up into two parts. All right? One last variation, and this maybe I'll just do a little intro. We got about 10 minutes. One last variation is here. Sometimes we do it sideways. This, in my opinion, is a little harder in terms of like variations goes than the other one. Sometimes you got to do it sideways. What I mean by that is something like this. This is one which looks, at a glance, it looks pretty normal. Oops. But it's actually not normal. Here is a line part and a sideways parabola part. So the line is y equals 1/2 x. And the parabola, the sideways parabola part is x equals y squared minus 3. This is a very weird kind of function. Like, actually, it's not even a function. It's because it doesn't have the vertical line test, if you remember. But anyway, I want this area here. All right. And this one, you actually can't do using the sort of little methods that we've talked about already. You will notice if we try to do, making those rectangles, maybe I'll erase my blue scribbles here. Look at what happens if I try to make rectangles from the bottom up to the top of this picture. Actually, these ones that I'm drawing here are more or less fine. Those rectangles, they go from the bottom one up to the top one, right? If you, though, try to continue this over to the other side, something bad will happen. All of these rectangles go from the bottom one up to the top one, as they should. But if I continue to the left there, going like all the way out to the nose, I'm going to get some rectangles that look like that. This here is bogus. Why? Because the top and the bottom here are actually the same function both times. Or like I said, actually it's not a function, it's this thing. But it's the same formula both times. And so if you were to try to do like this, the big E minus smalls thing, actually, if you're using the same one both times, you're just going to get zeros here, and you'll get 0 for the answer. But obviously, that's not a zero area, all right? So all of this is a problem, and it's because we have this weird sort of like sideways thing, which is not actually a function. So the moral of the story here is when our curve is this kind of x in terms of y, like this, right? This is kind of like a red flag. As soon as you see this sort of thing solved for x instead of solved for y, this is an indication that there's perhaps some funny business going on here. That's not an actual function of x. It's not a function of y in terms of x. Actually, it's a function of x in terms of y. So when our curve is x in terms of y, we do it sideways. And what I mean by that is, I'm going to draw the same picture again. So the line goes like this. The parabola goes like this. Sorry, this is not very curvaceous. But what I mean by do it sideways is we imagine all our little rectangles go like this. And now actually they work fine. Every rectangle goes from the line. Sorry, it's hard for me. I'm having a hard time drawing horizontal lines. But every rectangle goes from the line back up to the parabola, right? So actually this is going to work just fine. So what we have to do to actually work out the details here, sideways means solve everything for y, for x in terms of y. So I had x equals y squared minus 3. That already was solved for x in terms of y. But the other one, y equals 1/2 x, I am instead going to write as x equals 2y. So this right here, we can solve this for x in terms of y. X equals y squared minus 3 and x equals 2y. All right, and then we're going to do integral bigger minus the smaller, but everything using y's and a dy, where bigger means, usually when we do it, bigger means like the one that's further up, and smaller means the one that's further down. But since I'm doing it sideways in terms of y, bigger means further to the right, and smaller means further to the left, because to the right is where the positive values are, and to the left is negative values. So bigger means further right, and smaller means further left. All right. And the boundary values, like the a and the b, must be y values. So the a and the b on this picture would be here, that's the a, and here, that's the b, right? From down here to up here. So I imagine this as being an integral in the y-axis rather than in the x-axis, which is the way it usually goes. I integrate in the y-axis from a up to b. And we do the thing on the right minus the thing on the left. That's how we interpret the bigger and the smaller. All right? I want to work this one out in detail, but I think we don't have enough time, and since we're out of the weekend, you're going to forget anyway. So maybe we'll just kind of pick it up on Tuesday, finish this one off. All right? You should check out the class website. Within the next couple hours, you will see the homework assignment. It's going to be due on Wednesday. Hope you all have a good weekend.